A very good morning to all. I am Neeti Pahuja from Garg Engineering College, Department of CSE, and I am going to discuss the topic addressing modes today, which is a very important topic in computer organization and architecture. To start with, we'll discuss what is a computer instruction. So, a computer performs the task on the basis of instruction provided to it. Whatever we give it to the, we give the computer, it takes it as an instruction. So, instruction is basically a machine level code that the computer can understand, that the processor can understand, and then it can execute accordingly. So, I have written here as well, a computer instruction is a set of machine level code that the processor can understand and execute. So, before identifying the addressing mode, before discussing about these addressing modes, we need to understand the instruction. So, basically the computer performs everything in programs, and a program is a set of instructions. So, instruction is basically a machine level code that the processor understands that I need to perform this code according to this particular code. An instruction basically has three fields: a mode, opcode, and the address. The mode field specifies what is the mode of the instruction that we are going to discuss later in the slides. The opcode specifies what is the operation that I need to perform, which operation is going to be performed. There are multiple operations available with the ALU, like addition operation, subtraction operation, all the arithmetic logic operations that the ALU can perform. They have a specific opcode, and the size of this opcode depends upon what is the configuration for my ALU. And the last field is the operand field, or we may specify the address of the operand as well. So, either we can have an operand or we can have a address of the operand here. So, everything revolves around the address part of the instruction or the operand of address part of the instruction. So, opcode, it is the field that specifies the operation to be performed. Address field contains the location of the operand, that is register or memory location. Operand is basically the data on which we need to perform the operation. So, these operands, they may be stored in the registers for faster access, or they may be stored in the memory. So, what we need to do, we need to fetch the operands from the register to from the memory to the register, so that it can make the processing. Basically, the processing happens inside the processor, and processor has registers for faster access. So, we need to fetch the data, we need to fetch the operands from the memory to the register, and then we need to execute it. And the mode field specifies how the operands will be located, that we are going to discuss how many type of modes we have. So, starting with this, to understand the various type of addressing modes, it is important to understand how the computer deals with the instruction. Whenever the processor encounters an instruction, what does it do? It performs an instruction cycle. Cycle means the steps are repeatedly processed, and the first step is fetch, second is decode, and third is to execute. So, the computer performs it in the form of fetch, decode, and execute. Firstly, it fetches the instructions from the specified address which is specified there. From where it is located, we will fetch the address, fetch the instruction from there, and then we will decode the instruction according to the machine level code, then execute the instruction, because the system understands the machine level codes only. So, it will decode and will understand it, and then it will execute it. So, it is fetch, decode, and execute operation. So, the first addressing mode that we will discuss is the implied addressing mode. Implied addressing mode says that if we have an instruction of this type where we have an opcode and we have address field, in this address field we are specifying the operand implicitly in the instruction. I should change the color of the pen, so I guess it will be more visible now. So, in the address field of the instruction part, I will specifically implicitly say that this is the operator, or this is the operand on which I need to perform the operation. So, in this mode, the operands are specified implicitly in the definition of the instruction itself. For example, all the operations that we are going to execute, they are being executed, they are kept inside, all the operands are kept inside a special purpose register called the accumulator. So, we need to get the data from memory or from any other memory register to the accumulator, and from here the accumulator will send the data to the ALU, and it will be performed, the function will be performed in the ALU. So if I say an instruction, let's say complement the accumulator. Complement the accumulator means accumulator is the register which is processing the data and the data itself is in the accumulator. So I am not explicitly specifying the operand, I am implicitly specifying it inside the instruction only. So complement accumulator is a type of implied mode instruction. Fine. So instruction complement accumulator is an implied mode instruction. The operand accumulator, it is implied in the definition of the instruction itself. Another example may be increment the accumulator. Increment the accumulator, what this instruction will do? It will increment the content of the accumulator. So we will increment whatever content is available in the accumulator, we will increment that content and will save that content back to the accumulator register itself. So these are our implied addressing modes. Another example, zero address instructions. So we have a stack based organization of registers. If we are using stack based organization, there we use the zero addressing. Zero addressing says, for example, I have a stack of data, a stack of registers, let's say R1, R2, R3 and so on. Fine. And the data are kept inside these register. So if I say I need to perform add operation on the contents of the register which are saved in the stack, I need not to specify any address explicitly. I will only say add, and what the add will do? It will check for the stack pointer. Stack pointer is pointing to the top of the stack element. Which element is on the top of the stack? It will pop that element and will get that. And the add operation, it takes two operands. So once we will pop the element 10, the stack pointer will be pointing now to the next available location. So we will pop that element as well and we will perform the addition operation. So this is an implied addressing mode where we are not specifying the address explicitly, it is in the instruction definition itself. Next is the immediate addressing mode. Immediate addressing mode says, in this mode, the operand is specified in the instruction itself. Earlier, we were not explicitly specifying it, it was in the definition of the instruction, and now it is specified in the instruction itself. It is basically used to specify the constant values. If we want to initialize a value to a constant, initialize a variable to a constant value, so we use this mode. For example, the value, if I have some program, and in program generally we have two type of things, we have variable data and we have constant data. So the variable data, they keep changing their values inside during the execution of the program, but the constant value, they remains the same. For example, the value of pi, it remains the same throughout the execution of the program. So I can explicitly specify that this value is finite and this value is defined and it won't change throughout the course of the execution of the program. For example, add R110. What does instruction does? This instruction says that we need to add a value 10 to the content of register R1 and then transfer the result to register R1 itself. So this is generally, these values are specified by hash value. A hash value says that it is a constant value and it is not going to be changed during the execution of the program. So such instructions contain the operand field in place of an address field. So in an instruction, as I discussed earlier, we have two fields, an opcode field and an address field. And in case of immediate addressing mode, in the address field, we are having the operand value itself, the constant operand value in the address field. It is useful for initializing the registers to a constant value. As I discussed earlier, if we need to initialize a value c, which is the speed of light, that will be constant throughout the course of the execution of the program. But it has a limitation that the range of constant depends upon the length of the address field. For example, if I have 4 bits of this address fields, 4 bits for this, that means I can have 2 raised to the power 4, that is 16 values ranging from 4 zeros to 4 ones. So I can specify only 16 values in this address field. If I need to specify more, I either need to expand the address size, I need to expand the size of the instruction, or I need to use some other way. So this was the limitation for this. Next, moving on to register addressing mode. Register addressing mode, registers are the fastest memory locations available that we have in the computers. They are the fastest and the costliest memory locations which are available. A register, it is made of flip-flops, and each flip-flop can contain 1 bit of information. So when this register addressing mode is used, when here the address field of the instruction specifies a processor register, it is called register addressing mode. So in this instruction, what we are having the opcode field, and in the address part we are specifying the register number. What is this register number? Register number, we have many general purpose registers which are available to us in the processor, and each register, it is identified by a unique number which is given to it. It may be R1, R2 and so on up to Rn, depending upon how many registers do I have. For example, if I have 16 registers inside my processor, so I need 2 raised to the power 4, I need 4 bits to represent each of these 16 numbers explicitly, each of these 16 number exclusively, ranging from 4 zeros to 4 ones. Fine. So in case I have 16 registers, I need 4 bit to specify this number, and this 4 bit number will be in the address part of the instruction. If I say this will be like 0000, it is specifying register number 0, 0001, it is specifying register number R1, and so on up to 1111, which specifies register number 15. So if I say the instruction is add R7, add R7 says that I need to get the content from register number 7, whatever value is lying in register number 7, that is the value of the operand. This is register addressing field. The operands are in the registers that resides within the CPU. As I have discussed earlier, that registers are the memory location. These are the memory elements which are inside the CPU, and our operands are lying on the registers which are specified in the instruction. A k-bit field can specify any one of 2 raised to the power k registers. That is, if I have 16 registers, so a 4-bit field is required to identify one of the 16 available registers. For example, accumulator is accumulator plus R. That means the register value, the register number R, let's say this is R0, the register value, the register number R0, it is having some content, and that content is added to the content of accumulator, and the result is saved back to the accumulator. This will add the operand stored at register R0, to the operand stored in the accumulator. So what we do, if I need to perform add accumulator R1, that means what I need to do, I'll go to register R1, I'll go there and will fetch the value of the operand from there, and will add this value to the value of accumulator, and will transfer back the result to the accumulator itself. So this is register addressing mode. Next we have a variation of this, which is register indirect mode. The register indirect mode says the instruction specifies a register in the CPU. Let us understand with this diagram. This is a stack of registers, and we have some consecutive memory locations as well which are available to us. So these are registers and we have memory. So what it says, the instruction specifies a register, the instruction, its address part, it specifies a register in the CPU whose content, we will first go to the register stack, we'll go to register R2, let's say these were R1, R2, R3 and so on. We'll go to register R2, we'll check the value of its content give the address of the operands in the memory. So what it specifies that we go to register R2, we'll check the value, whatever value is lying there. This is not the operand. This is the address of the memory location where my actual data is. Got it? That means this register number specifies where I need to, which register I need to process. I'll open that register, will fetch the data from there. That data is not my operand. My operand is lying on the memory location which is pointed out by that particular register content. Is it clear? So if I need to, a register contains the address of the operand rather than the operand itself. So the register, the R2 register, it contains the address of the operand rather than the operand itself. That is why I am calling this as indirect register mode. Indirect register mode means I am not directly contacting the register. I am not directly contacting to a memory location either. I am contacting to a register. That register in turn is having the memory address. On that memory address, my data is available. This is the chronology. For example, if I process this instruction, move R1, R2, this specifies the memory content. So the value of R2, the value specified by register R2 is moved to memory location specified in R1. This square brackets, it specifies the memory location. So what it will do, it will add the content of registers content. On that content we will find, on that memory location we will find some operand, and that value will be added to, or that value will be moved to the accumulator. This is register indirect mode. Moving on to this register indirect mode, it has a special case which is called auto increment or auto decrement mode. This is a special case of register indirect mode. When we use this mode, if I have an array of locations, for example, I have a table of locations and all these things are fetched sequentially. Like I need to find out the value from memory location 101, then from 102, then from 103 and so on. I need to access all these values. So I use the auto increment mode. Or if I want to, like I have a for loop, this is a programming concept. I have a for loop and I'm going to use some values. I is equals to this I is equals to 0 to, let's say I is equal to 10. I need to execute the same code from ranging from I is equal to 0 to I is equal to 10. So first I will take the result from I is equal to 0. I fetch the operand from there. Then I'll increment the register value which is pointing to the memory location. Will fetch the value from there. Then again increment, will fetch the value, again increment and will fetch the value. This is auto increment mode. So this is similar to register indirect mode. Again it is not specifying the content itself. It is specifying the value of memory location where my operand is lying. So this is similar to register indirect mode, except that a register is incremented and decremented before or after its value is used to access the memory. When the address stored in the register refers to a table of data, that I said, when we have a table of data in memory, it is necessary to increment or decrement the register after every access to the table. Like I say add R1, that means add the content of R1 to the accumulator, or if I specify this, that means add the content which is available on the memory location specified by R1 to accumulator. And if I say R1 plus means now perform this operation, then increment the content of this register. For example, its earlier value was 20, so increment it to 21 and then go to that 21 location, fetch the data from there and then execute this data. This is auto increment mode. Same way we can implement the auto decrement mode as well. Auto decrement mode says start from some value and with each operation, with each consecutive operation, decrement the value. Once it is done, decrement its value and then get the code again. So next is the direct address mode. Earlier we have all discussed implied mode where the operand is implied inside the instruction only. Then we had indirect mode, we had immediate mode where the constant value was specified. Next, we had the register direct mode where the value of the operand is inside the register. Next, we had register indirect mode where the value of the operand specifies the memory location where my operand is residing. Next, I am having the direct address mode. It is in this mode the operands reside in the memory and its address is given directly in the address part of the instruction. So, this is the simplest case of instruction where the address of the operand, it is the address of memory location. I have this memory. Let's say I have 2048 blocks of memory available with me, ranging from 000 to how many number of bits we need. So starting from 0, 1, 2 and so on, we have 700 or maybe 2047. So the address field specifies the location of the memory where my data is lying. So for example, its value was 700, then 700 is not the operand, it is the value of memory location where my operand is lying. So the value of operand is 700. For example, it is add x. Add x means go to memory location x, fetch the data from there and add that data to the accumulator. If I specify like this, m of x, that means from the memory location x, I will fetch the data into the from the memory and then that data will be added to the content of the accumulator and finally the value is stored back to the accumulator. I guess it is clear. This will add the content at memory location x to the accumulator itself. If I say add 700, add 700 means go to memory location 700, fetch the data from there I will get 70 and add this content to the content of accumulator and transfer back the result to accumulator. This is direct address mode. Earlier we discussed register direct mode. Now we are discussing direct address mode, which means direct address of the memory location is available. Next, we have indirect addressing mode. Like we discussed register direct and register indirect. Here we are discussing memory direct and memory indirect. Memory direct means go to that memory location, fetch the data from there. Memory indirect means in this mode the address field of the instruction. Again, try to understand with the example, with the diagram. I have this memory available with me and every memory block is having some address and so on. So let's go by the line. In this mode, the address field of the instruction. So this is the instruction. We have the opcode and we have the address part. So the address field of the instruction gives the address. It gives the address. For example, let's say the value here was 400. It gives the address. It gives the address of the memory location. That means it gives the address 400. We'll go to that memory location where the effective address is stored in the memory. Where the effective address. Now what is an effective address? Effective address is the actual address where the operand is lying. Right? We have many type of addresses. So effective address is the ultimate address where the operand is actually lying in the memory. That is the effective address. So effective address in this case, we will first go to the memory location 400. Now the data on the memory location 400 is not the actual data. It is the address of some other memory location where my data is lying. So I will go to location 900, will fetch the data from there and this is my actual operand value. Got this? So the effective address in this case is not 400. We'll go to 400, fetch the value from there, then we'll go to that particular location which is actually pointing out the operand. So operand is saved in this location. So the effective address is 900. So there is a difference between address and effective address. Address means specify another address, but effective address is the actual address where the operand is being lying. So it is used to implement pointer and possible parameters. Pointers. So what the pointer is, it is a programming concept. Let's just discuss it. Let's say we have A ampersand B. That means we specify it with a star, with a pointer. So pointer is basically a variable that keeps the address of another variable. So A is a pointer which is having the value of another variable, B. Ampersand B specifies the address of B. So same way, this address, it is having the value of another address, and that address is having the value of the operand. So in case we want to specify pointers, if we want to use these, so we need to have indirect addressing mode. Here we need to have two memory accesses. This is the limitation, this is a disadvantage of this mode, that operations, two memory executions we need to do. First we'll execute the memory first one, and we'll go there and we'll again perform the memory fetching. Two types of fetching, two types of memory access we need to perform. So again, add x here means add x. It means we'll go to the memory location which is pointed out by the value x. We'll fetch the content from there and we'll go to that particular memory location, and finally we'll get the value of the operand. Now we will add that value to the value of accumulator and transfer back the result. For example, if x was, let's say, if x was 1000, so what we will do, we'll go to memory location specified here, the address will be having the value 1000. We will go to memory location 1000, we'll get the value from there, that is 700, and we will go to memory location 700, we'll get the value from there which is 70, and on that 70 content we will add it to the accumulator and transfer the result back to the accumulator. I guess this is clear now. Next is a relative addressing mode. Relative addressing means it is in relation to someone, it is in relation to some other value. In this mode, the content of the program counter, what is the program counter? So program counter is a special purpose register. It is again a register that holds the address of the next instruction being executed. I have a sequence of instructions, so the program counters there is a address register that holds the content of that holds the address of the current instruction being processed, and I need to have the next address instruction also saved in my memory. So it is the program counter that keeps the address of the next instruction which is being executed. So in this mode, the content of the program counter is added to the address part of the instruction in order to obtain the effective address. So what we do here, for example, I have we'll add this value to the value of program counter, and that will be the location of the operand. Here is the memory location of the operand. So effective address is the value of the program counter plus the offset value. Offset value is, for example, I am executing some code and these are the memory words which are written in the memory, and on this, let's say I have a value 500. On 500, we have these memory words. On each word we are having some instruction. So let's say the instruction is branch 550. That means move to now 550 location and start executing from there. So one way is to specify that branch 550 directly. Use the direct mode, use the immediate mode and specify the value 550, go to location 550 and start executing. But this is not feasible because the size of the instruction would be too big in that case. So what we'll do, we'll take some base register and its value will be fixed every time. When the instruction is being processed, we'll add this offset value to it and we'll go to that particular location. So this is relative addressing mode where we are specifying the address in relation to the base address. So this is our in address in relation to this program counter. So address, let's say the program counter is pointing to 825. That means the next instruction to be executed is lying at the location 825. Now the address part of the instruction says 24. That means which instruction is processing, it is on address location 824. We need to add some content to it. We need to add a value 24 to it. This is 2825 plus the value 825 plus the value 24, and go to particular thing, and then you will get the address where the effective address is from the computation 826 plus 24. 826, why? Because 825 was the current value which was being executed. Next we will increment the program counter because it will always hold the next address of the instruction which is going to be executed. So first we will increment it to 826, then we'll add it, then we will add the offset value to it, and it will give the address 840. Now we will go to location 840 and will start executing from there. This is relative addressing field. Similar to this is index addressing mode. In index addressing mode, we use a special register which is called the index register. The index register holds the value of index, and this index is added to the current value of which is being provided in the instruction itself, and will fetch the data from the value which is there. This is, in this mode, the content of an index register is added to the instruction part of the instruction, address part of the instruction to obtain the effective address. So the index register is a special CPU register. We have a number of registers available in the CPU. There are some general purpose registers and some specialized registers as well. So index register is a special kind of register that contain an index value. The address field of the instruction defines the beginning address of the data array in the memory. Each operand is stored in the memory relative to the beginning address. So the effective address where the actual operator is lying in this case is the address part of the instruction plus the content of this index register. If my index register says the value 700 and in the address part of the instruction I have value 30, that means my effective address is 700 plus 30, that is 730 is the memory location where my actual data is lying. This is the value of operand that I need to fetch. So it needs multiple registers to implement the addressing mode. I need index register, I need another base register as well. So one of these registers is named as index register that stores the value of index. Any array element may be accessed. The advantage of this is, for example, I need to address some values from an array. Like I have 101, 102 and so on, some values which are stored in a array. Array is a data structure for holding continuous values, same type of value. So if I want to access 101, then I need to access 104, then I need to access 110. So all the time I need not to specify the exact location. What I will do, I will save the value 100 to my index register. These all are relative to value 100. The starting value is 100, then 101, 102 and so on. So I'll save the value 100 to the index register, and whichever value I want to access, I will specify that value in the address part of my instruction. This is my instruction. I have opcode and the address. So in the indexed mode, in the address part, I will specify the value that I need to add to the index to get the particular location. For example, I need to access the operand. My operand is here at location 104. So what I will do, I will specify 4 in the address field. So this will be, effective address will be the address specified in the instruction plus the value of the index register, that is 104, and we will fetch the data from the location 104. If I wanted to access the data element from 110 location, so my address value will have been 10 and the final effective address will be the address part plus the index part, that is 110. This is again a special type of relative addressing. So the address, effective address is calculated in relation to the index value. Last we have base register addressing mode. In this mode, the content of the base register is added to the part of the instruction to obtain the effective address. When we use this type of addressing, it is basically, see what we have some programs in our RAM which are saved in our RAM, let's say P1, P2, P3, and the size of the RAM is limited. So what we do, when we need a program, we put it in the RAM and then we swap it out. Then again when we want it, we put it back in the RAM. So this swap in swap out process, it goes on. It is a concept which is discussed in operating system. So this swap in swap out, what it means, now it is given some memory location. For example, I have this P1 which is being executed from location 100 to 199. There was a code for the program and the instructions were in sequence from 100 to 199. At some point, let's say I had an instruction branch to 160. What I wanted was, I will in this particular instruction, I will say that go to particular instruction number 160 and perform the operation which is specified at 160. So this is how it does. It is very easy. We'll go to particular jump condition. We will use that jump condition. We'll go to that address and we'll execute. Simple. But problem arises when I remove this process from the memory. I removed it. The memory space became free. I allocated it to somebody else, some other program. Again, this process came in and this time the same address is not allocated to it. The address which is allocated to the program is 4002, let's say 499. So this is the program that this is the location that I have been allocated now. So in this, again, my absolute address is given, which is branch to 160. Now it will go to location 160, which is actually the address of some other instruction. It is not in the sequence now. So in such kind, we will give, in such kind of scenarios, what we do, we use the value of a base register. Base register means from where my instructions are starting. In this case, the base value is 100. In this case, my base value is 400. So the base register is assumed to hold the base address, the first address, and the address field of the instruction gives the displacement relative to this base address. In this case, the displacement was 60. So I can specify 100 plus 60. We'll go to that particular 160 statement. In this case, this would be 400 plus 60. That means go to statement 460 and start the execution from there. So this is base addressing mode, where this first address is saved in the base register and then the next codes are executed. So the base register addressing mode is used in computers to facilitate the relocation in the memory. Relocation of the program means once we swapped it out of the memory, then we are getting it back in the memory and use this base register organization to specify the address. That's all for the addressing modes. Thank you so much for listening it so patiently, and if you have any doubts, we can discuss it through the mail ID or maybe, and the next we'll discuss in the next lectures. Thank you.